Good afternoon. Thank you for coming or staying for the last session of today's events on quantum materials and devices. My name is Petar Đurić, and I am Chair of Electrical and Computer Engineering. Before I introduce the speaker today, I just want to make a short comment that I was very happy to see a good number of our faculty in Electrical and Computer Engineering and students attending the events. Our speaker in the last session is Professor Dmitri Kharzeev. He's Distinguished Professor in Physics and Astronomy. He's also associated with Brookhaven National Labs. He'll present a talk on that is on the screen, with title on the screen. We also have a panel, and I'll start from this end. Gabriela Carini, BNL. Chuck Black, also BNL. Shu Du, he is a professor in Physics and Astronomy, and Sergei Suchalkin, professor in Electrical and Computer Engineering. So without further ado, Dmitri Kharzeev.
Thank you very much. So I'm really delighted to be here today, and it's been a great day of fantastic talks so far. And what I will do in this talk is I will discuss a new idea for the next generation of devices for quantum computing that we are developing together with my colleagues at Stony, Brook, and Brookhaven. So I want to stress that this is one of the many ideas that are being developed in parallel, but I think it illustrates the amount of cross-disciplinary interactions that I think has to happen to make progress in this exciting field. So all new things have to be built on a solid foundation. And as you have heard today, much work has been done in recent years on superconducting devices for quantum computing. And so this is why I would like to start with superconducting devices. So superconductivity was discovered a long time ago. This is the plot from the original paper by Kamerlingh-Onnes from 1911. This is the image of a magnet levitating over a superconductor. And it does so because the superconductor repels the magnetic field. And it repels it because the photons that compose magnetic field get massive inside a superconductor by the mechanism which is completely analogous to the mechanism by which electroweak bosons become massive in the vacuum of the Standard Model due to the condensate of the Higgs boson, which was a recent discovery in high-energy physics. So this illustrates that discovery of superconductivity was a truly fundamental discovery that affected several fields. So now, all truly fundamental discoveries are incredibly useful. And we already discussed this before, but we don't have to look far for useful application of superconductivity. So this is the work that Paul Lauterbur did here at Stony Brook, where he developed magnetic resonance imaging in the 70s. And this made possible by superconducting magnet coils that enable magnetic resonance imaging. And so this is a technique that truly saves lives, and as I personally had a chance to discover not a long time ago. And so every time we benefit from such things, we have to remember that we really owe this to a fundamental discovery in physics. So here is my friend John Ferretti from radiology department performing the procedure on a patient at Stony Brook Hospital. So now the superconducting devices are yet another applications of superconductivity, which is made possible by the intrinsically quantum nature of a superconductor. So this is the paper written by Tony Leggett, a Nobel laureate, and Anupam Garg at Urbana in 1985. And the title of the paper is Quantum Mechanics versus Macroscopic Realism. is the flux there when nobody looks? So the title is a reference to Einstein's objection to quantum mechanics. And Einstein famously said that he cannot accept quantum mechanics because he likes to think the moon is there even if I'm not looking at it. So this is the notion of macroscopic realism. And just to illustrate the essence of it, if you look to at your neighbor to the right, and then close your eyes, and then open your eyes, you know that your neighbor will still be there, unless, of course, you open your eyes after my talk is over and everybody leaves. But if you open your eyes, let's say, after a second, you know your neighbor is there. And you also know that your neighbor is there whether you look at her or not. And this is the essence of this macroscopic realism. So we know that quantum mechanics, as Seth told us, is weird. And so these quantum particles flicker in and out of existence. But macroscopic objects are supposed to behave in a nice, predictable way. And so what Leggett and Garg argued in this paper is that even macroscopic systems, such as superconductors, can also behave as quantum mechanical states. And in particular, they can be in the superposition of two different states. And this is illustrated here with this Schrödinger cat, which Barry Sanders explained to us beautifully earlier today. So now the Leggett and Garg also proposed a way to observe this superposition of macroscopic states in a superconductor. And the experiment, which is illustrated here, it is a superconducting quantum interference device. This experiment was for the first time performed here at Stony Brook by Professor Lukens and his group. So the system has two minima, and one minimum corresponds to current circulating clockwise, another to the current circulating counterclockwise. And they were the first to observe the quantum tunneling between these two states, which is completely not trivial because the system involves billions of Cooper pairs, the bound states of electrons. So the transitions between different states within an individual well were observed before by Professor Martinez and his group. And the group of Martinez now has become the core of the Google program on quantum computing. But the transitions between different wells were first observed here by Lukens' group. So later in 2000, they demonstrated that one can indeed build quantum superpositions of these two distinct macroscopic quantum states, really getting as close as one could get to realizing Schrödinger's cat, which is in a superposition of a live and dead state. So this is how this superposition is realized. And in the presence of quantum tunneling between these states, the clockwise and counterclockwise states get the energy degeneracy gets lifted, and anti-symmetric and symmetric superposition have different energies. So this made it to the cover of New York Times. And indeed, this article explains quite nicely this similarity between the experiment that was performed at Stony Brook and the Schrödinger's cat. And I should also point out that quantum computing is not the only possible application of this idea of quantized flux, because as was also done here at Stony Brook originally, one can build a computer in which the bit is represented by the state of magnetic flux in the superconducting loop, which is quantized. And so let's say if you don't have any flux in the superconducting loop, you say it's 0. If you have one quantum of flux, you have 1. And you can build a logic based on this representation. And this has become known as rapid single flux RSFQ logic. And the group here, led by Konstantin Likharev, in fact still holds the world record in the clock frequency with this RSFQ device, which is about 770 gigahertz, about 2 orders of magnitude higher frequency than the world record for conventional semiconducting devices. So this is nearly terahertz frequency, and this terahertz will reappear in my talk later today. So these developments led to this early conference and quantum and reversible computation. And again, you heard today from Barry Sanders about reversible computation. Professor Karepin was the chair of the organizing committee of this conference. He still looks the same after all these years. And many of the participants of this workshop, including Seth, are still here in the room today. Okay, so of course, a lot has changed since 2000. And there has been really impressive progress in the coherence time of this superconducting qubits. So this is so-called Sholkov's law of the growth in the qubit coherence lifetime. And the modern devices really push this coherence time to almost a millisecond. So now the physics behind creating these quantum superpositions of different states in superconducting qubits, as I explained, is the physics of quantum tunneling. So here is another realization of so-called charge or transmon qubit in its later realization. So you have 2 Cooper pair islands separated by this Josephson junction. And then the pairs can tunnel through this junction. And the wave function of this system is a coherent superposition of states with different number of tunneled Cooper pairs. So this is this quantum superposition. So now, for those of us who are used to high energy and nuclear physics, this really looks like the structure of the vacuum of some non-abelian gauge theory, such as quantum chromodynamics or the standard model. And in this analogy, transitions between these individual states are, for example, responsible for the baryon asymmetry of the present universe, why we live in a universe which has more matter than antimatter. So it appears that the mathematical structure of both systems is really identical. And just to illustrate this, here is the spectrum of the vacuum of quantum chromodynamics. This is from an old paper by Rob Pisarsky, Michel Tingai, and myself. And this is the energy spectrum of transmon qubit. So you can really go carefully through these calculations and convince yourself that the math and the underlying physics are really identical in both cases. So now the question is, can we use it somehow? Can we answer the question that was asked about an hour ago? Can we get to mass producible quantum computer that each one of us can put in our pocket or at least in our briefcase? So now the present superconducting devices require refrigeration down to millikelvin temperature. And so unless you are willing to carry a dilution refrigerator on your back, you would not be able to put a quantum computing device in your pocket. So the question is, can the basic physics of superconducting qubit be realized in a different system, potentially capable of operating at room temperature, higher frequency, and at least as good ratio of coherence time to gate time? And so here is where we can use this analogy between the physics of superconducting qubit and the physics of the standard model, where you can have eternal transitions not from left island to the right island, but you can have a similar transition from left-handed chiral fermion. And chiral fermion is a particle with spin 1/2. And its spin can be either parallel to its momentum, in which case it propagates through space as a right-handed screw, or anti-parallel to its momentum, in which case it propagates through space as a left-handed screw. And this is illustrated here. And these chiral fermions are described by Dirac, Weil, and Majorana equations. And so this physics of Majorana fermions is, as you heard today, is used by Microsoft in topological quantum computing. But what I'm going to tell you today is the physics that is based not on Majorana fermions, but the physics which is based on so-called Weil fermions, which are conventional massless fermions that have their antiparticles. So the chiral, the transition between left-handed fermions and right-handed fermions can happen if we put these fermions in external electromagnetic fields. For example, if we put them in parallel electric and magnetic fields, then we can transfer fermions from left-handed states into right-handed states. Or we can achieve the same by shining a circularly polarized light on these fermions. So now what happens then is that if you put this system in an external magnetic field and create a system in which all fermions, for example, are right-handed, then you see that the spins of positive fermions always will point along magnetic field. The spins of negative fermions will always point against magnetic field. But chirality, as I said, is a projection of spin on momentum. And so this means that for positive fermion, being right-handed means moving up. For negative fermion, being right-handed means moving down. And this means that positive and negative fermions move in opposite directions in space. And this means that you generate an electric current. So this is an analogy of this superconducting current that I told you about before. So it appears that this analogy to superconductivity is quite deep. And if you look at equations describing electrodynamics of both systems, then even though there are very important differences, by large, the electrodynamics of superconductors and the electrodynamics of these systems of chiral fermions is very similar to each other. So now all of these developments were really done originally for the physics of core-gluon plasma, which we just discussed 30 minutes ago. But it appears that we don't necessarily have to wait for the outcome of high-energy experiments to check what happens. We can make use of condensed matter systems which also possess this chiral fermion quasi-particles, as was originally predicted by another Nobel Prize winner, Brikosov and Benislavsky. So this physics was also discussed by the recent Nobel laureates in physics, in particular Duncan Haldane. And what happens in these systems is that due to a particular symmetry of the crystal, they support quasi-particles that behave exactly as massless fermions, and massless fermions that possess a definite chirality. So this means that these materials can be a base for generating and studying these chiral currents that I told you about before. So this is exactly the physics that we studied here with my collaborators from Brookhaven, Chen Li, Tony Valla, Genda Gu, Stony, Brook, and Princeton, and Berkeley in this particular semi-metal zirconium pentatelluride. And we have indeed observed this current. And you can detect it by placing this crystal in parallel electric and magnetic field, which, as I told you before, creates an imbalance between left-handed and right-handed fermions. This imbalance gets translated into electric current. And when electric current grows, you can detect it through the effective decrease of resistivity. So by now, there are dozens of materials that exhibit this kind of behavior. And here comes the idea. So as I told you before, the physics of these chiral currents is quite similar to the physics of superconductors. And just like we used the currents, persistent currents in superconducting devices, we can now envision a ring made of this chiral material in which the current would circulate clockwise or counterclockwise or in a quantum superposition of these two states. So now you may say, what is the coherence time of this device? And here I have to disappoint you because the coherence time is extremely short. So in these materials, the best of these materials that we have at hand, this is a coherence time of about a nanosecond. And I told you before that superconducting qubits are now pushing the millisecond coherence time. So you can say this idea is completely crazy. It can never work. However, what you have to remember is that what matters is not the coherence time per se. It is the ratio of coherence time to the time over which you can implement a quantum gate. And the time over which you can implement a quantum gate in a superconducting qubit is limited by the superconducting gap. So loosely speaking, binding energy of the Cooper pair. Whereas in these materials, the time over which you can manipulate this current is lower than 1 picosecond. And this is what I'm now going to illustrate. So this is the effective Hamiltonian. It is indeed quite similar to superconducting qubit. This is the simplest form to which you can reduce this Hamiltonian. You can also work out more detailed expressions for a three-dimensional case. So now whether we can manipulate these currents on picosecond scale. And this is the recent experiment by Min-Kun Liu here at Stony Brook and Jinbor Chi. And what is done here, we have a vial semi-metal, tantalum arsenide, and they shine on it with this nearly optical laser. And the light is circularly polarized because this is what we need to create chirality imbalance. And you can see that this time-dependent chiral current emerges, and it is a quantum superposition of left and right chiral states. So now look at the scale on the time axis. It is a picosecond scale. So you really have to tune the energy of this laser quite carefully to achieve this. So the theory work for this paper was done by my students Sahal Kaushik and Evan Philip. And there is some really interesting physics involved, which for my high energy colleagues is analogous to what happens when a heavy quark decays through a weak process into a light quark. The velocity in this process gets changed over a short period of time, and this induces a large amount of coherent Bremsstrahlung radiation, which is what is detected in this experiment. So now, just following in the footsteps of Professor Lukens, since we know that these two states are connected by tunneling, we can form symmetric and anti-symmetric decomposition. We can control it by circularly polarized infrared light or external magnetic flux if we are talking about thin rings. And we can try to turn this into a working device. And this is the idea that we are pursuing together with my colleague and friend from Brookhaven, Chan Lee, who is in the room. So now, does this have a chance to work? So the answer at this point is not known, but I think it's quite possible because these qubits can operate at high temperature. We saw that this measurement with the control of these currents was done at room temperature. These currents can be controlled at high frequency of about 10 terahertz, which is 4 orders of magnitude faster than you can control current in superconducting qubits. Coherence time is short, but again, the gate time is much shorter. So the ratio of coherence time to gate time can reach about 10 to the 4th, at which the quantum correction algorithms about which you heard will work. And there are some other potential practical advantages of this. But clearly, a lot has to be understood and done before we really can hopefully make this a working device. So now, obviously, to understand and do things, you have to rely on expertise of your colleagues. And I'm really happy to say that we have a lot of expertise in this particular field, and as well as any other field in physics here at Stony Brook. So here is Jennifer, who is an expert in wire semi-metals. Shudu, who is in the panel, a real expert in 2D and 3D chiral materials. Sergey, who is in the panel, is an expert in nanofabrication of these 3D materials. And Alexander, with whom you interacted just a little while ago, is an expert in all kinds of chiral states and the boundary chiral states that occur in these systems. So I would also like to emphasize to go back to the medical imaging from which I started, and to say that we also now have a very productive collaboration with Hassan Arbab from biomedical engineering, with the goal of developing a terahertz imaging for cancerous tissue and precision surgical guidance based on these physical techniques. So this is the work by Hassan, Shudu, Menkun Liu, and myself. And this work is supported by a very generous private donation by a Renaissance employee and his wife. So this is yet another illustration of how the local community supports what we do. So here is the outlook. So I think no matter whether this particular idea works or not, I think we really need radically new ideas to make the next big step in quantum computing. And I think it's also true that to generate and to develop these ideas, will require an effort of experts in different fields of science. And this is what we have here at Stony Brook and Brookhaven. I think this is really the strength of this place. And we have here everything in place for making a big impact on this exciting developing field of quantum information. But of course, we need to discuss how to coordinate our efforts. And I think this wonderful event is a very good step in the right direction. So I will stop right here. Thank you.
Now it's time that we hear from our panel members. We'll start with Gabriela.
Sure. Okay, can you hear me? Yes. So I work at instrumentation at Brookhaven, and at instrumentation we really develop all sorts of instrumentation. Has to do with very large detectors, for instance, for neutrino search, or X-ray detectors, where we try to put lots of electronics to make them as smart as possible, or even small things like using electrons to manipulate barium for produce the background of experiments such as neutrinoless double beta decay. So it's a very broad range of activities. And QIST came on my plate as soon as I joined Brookhaven 1 year ago, roughly. And one of the questions was like, what Brookhaven can do in this field, what can really do to advance, and what we can bring. And one of the first things was actually a visit to Eden's lab a bit less than a year ago. And I think everybody knows that enthusiasm is kind of contagious. And we started to work from that time on. And when I saw the lab, I thought, OK, what we can do here is really helping to scale things up, because that's what we really have done for many years. And scaling things up in this case is really try to bring what they have done so far to the level of size and capability to enable sort of quantum simulations, or also large-scale experiment for energy physics or things like that. So I'm happy that now Eden is with us and is putting together a quantum information technology lab. So that's one of the things we are seeing now, many plans and ideas coming together. Another example, for instance, is many years ago at Brookhaven, to improve the performance of one of these large detectors for neutrinos, we thought that it was better to put the electronics very close to the sensing anodes. And that meant to have electronics working at liquid argon temperature, cryogenic temperature. And this is an expertise that we developed. There was lots of R&D associated with that. And we're thinking, and we started to work on seeing how we can bring this expertise to use electronics close to qubits to control qubits at much lower temperature. So more generally, I would say what we're really doing and trying to push forward is to develop technologies and push technology in a direction that can make many of this quantum stuff that we have today happening and having a successful outcome of that, because ultimately it depends on the technology. So.
Thank you. Chuck.
My name is Chuck Black. I'm the director of the Center for Functional Nanomaterials at Brookhaven, which is Brookhaven's nanoscience department. I think many of us in the room have interacted with the CFN in some way because we are a national user facility for nanoscience, meaning that we're meant to be a resource for everyone. And most of the comments that I'm going to say in these few minutes here are also going to reflect a lot of the thoughts that our colleagues in the NSLS2 have also been having over the last few months, as the user facilities have been asked by the DOE to think about how will we contribute to this initiative in quantum information science. So we, like all of us in the labs, were asked to consider this question about a year ago. And speaking only for the CFN for the moment, NSLS2 people can tell us if they felt the same. many staff members, when we were asked to do this, kind of had a panicked look on their face. They realized, what do you mean we're supposed to contribute to QIS? Because we don't do QIS. We don't know what that means. And so there was a short period of time where we felt like we had concerns about how we could contribute. And so we've spent a lot of time in the last year interacting with groups like this one and many others, and having a lot of visitors and gaining confidence that actually, in fact, we have a lot to contribute, both today and tomorrow, because the reality is this is a materials problem. And the materials that we have to do the things that we'd like to do aren't sufficient. And that gives us great comfort, because if you talk about material science, that we do know how to do, and we've been doing it for a long time. So we're very excited to bring our talents to bear on these materials problems. And there are things we can do right away. As we talk to the pros who are really trying to make this go, even at some of the best places we've heard about today, they all say there are things about our materials that we don't know, and there are things that we wish worked better. And immediately we say, we can help you with that. And that's very exciting for us. But it's only the tip of the excitement, because there's a lot of other things we can do. There are a lot of things that people working to try to bring these devices to reality wish they knew about their material. They say, if I want to make a qubit out of this material, the only way for me to know if it's going to be a good qubit material is to make a qubit out of it and see if it works. And that, for those of us who do material science, that kind of annoys us, because it shouldn't be that you have to make the full thing and do all of this. Like, there should be things that you can measure about your material that will tell you if it's going to be good. And so we're excited not just to do the measurements we already know how to do, but to think about new ways to measure materials. So that's excitement number 2, but I've saved the best for last, because the most exciting thing for us, and I think for many of us, and we heard a little bit of that in the presentation just given, is that we believe, and I think many of us believe, that the materials that we will ultimately do quantum information science with don't exist yet. And that all of the progress that we've made until now has been made with materials that we just happen to have. Like the materials that IBM is using to build their quantum computers, they have been using these materials since the 80s. And these were materials that they used at that time for a completely different purpose. There was no quantum computing then. There was Josephson logic. We heard about it before. So it's our belief, and many people's belief, that if you want to build a material to do quantum information science, you should take a step back and think about what would you want in that material? What properties should it have? And build the material with those things in mind. That's a tall order. It's very ambitious, but it's something that we should do. So we're super excited about it, as you can tell, and we're looking for others who want to participate in something like that. So as we're getting our acts together in Brookhaven, our local partners are our strongest partners. So very glad to be part of this discussion today, and I think it's only the starting point.
I just want to echo on what Chuck just said. So my name is Sudu. I'm from physics and astronomy. So I work on condensed matter experiment and mostly on 2D materials. So previously, what I've been mostly my effort was mostly on trying to study how essentially the so-called charge transport, how electrons move inside these 2D materials. For example, we can do those characterizations in 2D materials in extreme environment, like a very high magnetic field, very low temperature, or we also combine these materials with other materials, for example, superconductor or some other functional materials. So with this new quantum wave, we try to, we are particularly interested in several questions, mostly we are wondering whether we can take advantage of the 2D materials, for example, in these quantum devices or quantum qubit. So I think this is very relevant to what Chuck just said. In fact, there's not too many work in this field. So for example, many of the 2D materials are they're crystalline. They're actually very high quality crystals, and they can also they can essentially be freestanding, say get separated from the substrate, maybe to some extent separated from the environment. So whether in such a device, whether one can achieve better coherence or better controllability. So all these are questions, I think, very interesting for us. And also, these materials can have their own properties. For example, there's chiral material, as Dima just mentioned. There's topological materials, and maybe these properties may have something good for the application in the quantum information science. So, so I can just give you one example. What these days we are working on is try to make use of this so-called edge state. So if you imagine you have a 2D material, you cut an edge, then you have this edge state. And in many of these systems, the edge states are the so-called topologically protected. So they have very nice uniform properties. Then we can make structured edge state. And these actually, we show that these edge states can behave kind of like artificial atom. Then what if we combine this artificial atom together and make them couple to each other? So we might be able to make something like a quantum simulator or even qubit. So I think this is very exciting time that we can make use of these new materials and for quantum applications.
Thank you. Sergey.
Hello, my name is Sergey Suchalkin. I am with the Department of Electrical and Computer Engineering and the part of the optoelectronic group. So the major activity of the optoelectronic group is design, fabrication, and characterization of new materials and new optoelectronic devices. And one thing I'd like to say a couple of words today is recent, I wouldn't say breakthrough, recent technology advances in a group which made it possible to create a new class of semiconductor materials, so which definitely can host some kind of exotic state of matter, like a Chern insulator, topological insulator, or quantum spin Hall insulator. So the basic idea is we are using molecular beam epitaxy to grow the high-quality crystal material. But this method has an important constraint. So we grow the material on top of some perfect crystal, which is called substrate. And there's a fixed number of substrate. So the material which we grow inherit the latest constant of the substrate. So generally, the material system we are working with is aluminum, gallium, indium, arsenite, and dimonite is a material with tremendous design flexibility. All type of band alignment can be realized there. The only constraint is if you try to mix up this material, you actually, let's say the crystal lattice of your alloy will be different. It doesn't fit the existing substrate. So if you try to grow the material with different crystal lattice off top of the substrate, the threading dislocation just destroyed your material. So what we have developed is a new method, which makes it possible to create high-quality crystal materials with virtually any lattice constant. So we can, let's say, leave this substrate constraint. So now, generally, what we can do, we can grow bulk material, we can grow 2D material, we can grow semiconductor alloys with controllable atomic ordering. So, and this material gives us tremendous possibility to tailor for example, the carrier spectrum. We can realize 2D structure which has a dispersion similar to graphene, this Dirac type material, like bilayer graphene. We can actually do some kind of exotic anisotropic material which has parabolic dispersion in plane, in a gross direction, and linear dispersion in plane. So all the thing, another good point about this system that it's effectively, it naturally has good interface with a superconductor. So it's opened the amazing possibility of creating composite device, like proximity coupled device of topological insulator and superconductor. We can think about magnetic doping of this material, and so on and so on. So generally, we're very happy to have amazing crystal grower, Dr. Kipshidze. So, and we are generally we are going to collaborate with other researchers and research group. What I would like to mention also is another asset of the group is very well-developed collaboration network. I think this way, the problem, experimental problem and technological problem are too complex to be solved within one research group. So we have very well-developed network of collaboration with National High Magnetic Field Lab, with Army Research Lab, Jet Propulsion Lab, Georgia Tech, Georgia Institute of Technology, and I hope, let's say, after this inspiring meeting, we'll, let's say, make this list of collaborators even larger. Thank you.
Thank you all. Now it's time to get questions from the audience. Yes.
Should I go? So yeah, I was wondering in your qubit, sort of your model for qubit, what are the native gates? And in particular, how do you carry out entangling 2 qubit gates? And I also was wondering how scalable your qubit system is compared to other existing qubits.
So this is a question to me. Okay. So the gates are implemented here by coupling these qubits to circularly polarized infrared radiation, because the circularly polarized light will get absorbed by these charged fermions. As a result, the fermions will change their chirality. And so, for instance, if I had initial state which was in a pure clockwise chiral state, then after I shine on it by circularly polarized light, I will turn it into superposition of clockwise and counterclockwise states. So the way in which gates are implemented in this system are actually very similar to what has been done before with superconducting qubits. So this is the biggest difference between this realization and Majorana fermion realization, because in the case of Majoranas, you really have to rely on this braiding, and you have to really reinvent how you implement the gates. Here, the only difference is that instead of relying on microwave radiation, you move into terahertz frequency range. And speaking of entanglement of several qubits, so this measurement of terahertz radiation that I showed in the talk was done using the near field, terahertz field. And so this means that the multiple qubits can be entangled, at least in principle, using this near field technique.
There was a question from Frederick.
Well, Lila asked my question. So.
Any other questions?
This is essentially a follow-up question to Dmitri. If there is such a big analogy between superconducting devices and these new chiral material devices, can you borrow architecture from the previously developed devices?
Well, you can borrow the principle of realizing these devices. However, let's say in the case of superconducting qubits, you really entangle them by coupling them to a microwave cavity. And with the terahertz radiation, obviously, this will not work, and it has to be modified. So there are some sort of differences in details of the implementation, but mathematically and theoretically, these are the same gates. You just have to think of different devices, for example, for entangling them.
You addressed a little bit the issue of matching the decoherence time to the gate time. But what are the advantages of these systems compared to the standard, the old-fashioned superconducting systems in terms of quantum noise? Are these much more robust towards quantum noise? And
Okay, that's a good question, and obviously I cannot claim that these systems are robust against noise. So there is an amount of protection of these currents, but this protection is only as good as the conservation of chirality in these materials. And in the materials that we have at present, chirality is conserved, but only approximately. And so going back to this discussion which we just had, what we really want from our materials colleagues is we want materials in which the coherence time of this chiral states is maximized, when the frequency of chirality flipping transitions is reduced below gigahertz, let's say. So if these materials are available, then of course we will be robust against noise, but before that, obviously, these devices are also subject to noise, just like superconducting qubits are, just on a different frequency scale.
Yeah, you might have answered this already. I just wanted to ask, how are your rings talking to each other? I mean, what's the mechanism for?
Yes. Yes. So as I showed in this experiment from Menkun Liu and colleagues, so the chiral currents, when you switch the current radiates in the terahertz frequency range. And there is a lot of near field terahertz field surrounding this current. So if you put several qubits together, then they are going to communicate through each other through this near field communication in the terahertz frequency range. So one can also think of some analog of microwave cavity, but then it has to be something which would be able to reflect this light in the terahertz range. And so this is again the question to materials. So there is a lot that we really need from people working on materials in this regard.
In the talk, you mentioned the analogy to a heavy quark
yes.
and a light quark. I guess the light quark is your chiral fermion, so who is the heavy quark?
Okay, let me explain this. This is actually interesting. So the point is the following. So the frequency of this light is tuned in such a way that it induces transition from the linear band, while band, where the fermions disperse as massless particles. So this is my chiral fermion, to the excited band, which is parabolic, and on which the velocity of this quasi-particle is very small. So this is my heavy quark, and this is my light quark. So what happens here is I excite this light fermion onto this excited band with much smaller velocity. As a result, there is a very substantial change in velocity of the quasi-particles. And as you know very well, when a charge suffers this abrupt change in velocity, it radiates a lot of Bremsstrahlung radiation. And this Bremsstrahlung radiation is this near-field terahertz that we want to use to entangle these qubits.
And just as a follow-up on some of the other
yes.
questions, what are the... Here's the resource. So what, what are the prospects of finding new materials? Is this like something, last week you realized we're going to need new ones? Or, where's that going?
As was already said before, the progress in this field often defies any expectations. And just to illustrate it, let me tell you a story. So, some years ago, we organized a workshop in Seattle on this chiral materials, and one of the participants was Kostya Novoselov. This was 3 years before he got his Nobel Prize, so he was just a sort of regular participant. And I asked him, So you did so much of this nice work on two-dimensional chiral structures. When can we expect from you a 3D structure? Because I always wanted to implement this anomaly in a 3D chiral material. And Kostya laughed and said, well, I don't know, maybe 15 years. And just a few years after that, this 3D chiral materials appeared. So, you know, I would not be surprised if a couple of years from now, someone grew a material in which the lifetime of chiral fermions were an order of magnitude or 2 orders of magnitude longer than it is today. But even with currently available materials, I think it's already kind of maybe feasible.
Hello. Yeah, with these superconducting rings, when you try to do them macroscopic, what is the issue? Why are you losing a qubit?
Okay, so the point is that in a superconductor, you have a persistent current, and as long as the current is below the critical value, it persists, right? That's why we call it persistent current. So the chiral currents persist as long as chirality of this fermion is conserved, because chirality is projection of spin onto momentum. And so if impurities do not flip the spin, this means that they are also not allowed to flip momentum, so the current will persist. But the problem is that chirality is only an approximate symmetry of this Hamiltonian, which also includes the terms that flip this chirality. So this chirality flipping terms is what limits the coherence time of this qubit. And what we want, again, from materials is we want materials which suppress this chirality flipping terms.
Any more questions? Actually, I will ask the last question, the same question, but for the panel about the materials. What are your thoughts on it?
I'm glad you asked that question because I felt like I should have chimed in with an answer to a question that came over here. And I feel like it's worth saying that whether we like to admit it or not, oftentimes new material discovery is just kind of, you try a bunch of materials and then one of them after a while works. And that what we've been thinking about as an opportunity in this case is to try to be a little more thoughtful about it, try to come up with probes that would allow you to measure the properties that you care about in systems like this, and we heard, you know, some of the things that you would care about, and to try to somehow in a smart way integrate that into the synthesis of the material itself. So this is something, you know, historically that's been done by, you know, researchers carrying the sample around and doing feedback this way. There's an opportunity with the confluence of techniques of in situ characterization and computer science and data analysis to fully integrate this into the loop, to try to use the characterization as part of the synthesis. But first you have to figure out what you care about and figure out how to measure it and integrate it all together. So this is the grand vision behind this idea that, hey, let's think about what would you want in your quantum material, what would allow it to perform, and try to design it that way from the start.
Okay. I would like to thank Dmitri again for the presentation and panel.